How we doing, guys? Looking at just carrying on exercise 9D in fundamental applied maths. We're going to look here at question 15, 19 and 21 on pages 173, 175. So we'll start with question 15. A cone of diameter 4 meters and height 6 meters is held immersed in oil with its axis vertical and its vertex uppermost. So they give you a diagram. Vertex is 1 meter below the surface. The relative density of the oil is 0.9. Find the magnitude of the buoyancy force, the thrust, which is the upward force on the flat surface at the bottom, and the thrust on the curved surface, which is the downward force on the flat surface. So let's start off with just the volume of this cone, which is 1/3 pi r squared h. So that is 1/3 pi. The radius is, see there, diameter 4, radius 2. Squared, and the height is 6, and that is all going to come out as 8 pi meters cubed. So we'll need that. The first thing they've asked for is the buoyancy of the acting on the cone, and according to Archimedes' principle, the buoyancy is equal to the weight of displaced liquid, not water. Okay, so the weight of the liquid is its volume times its density, that gives you the mass of liquid, times the acceleration due to gravity. So the volume of displaced liquid is the same as the volume displaced by the cone, is 8 pi. The density of this liquid, well, if it has a relative density of 0.9, then it has a density of 900 kilograms per meter cubed. Okay, so just multiply by 1,000 to convert them. Density of water, so that's times 900 kilograms per meter cubed, and acceleration due to gravity. Okay, so that all comes out as 7,200 pi g newtons. Buoyancy is a force. It's an upward force that will either make something float or make it lighter than it would be were it in air. Second part says find the thrust on the flat surface. So flat surface in the bottom. So thrust is a force caused by pressure. So pressure in liquid acts in all directions. So this thing is feeling it, I suppose, at every point on its surface. The net effect of all this pressure here is to push the thing up. And the net effect of this pressure here is to push it down. So this is called the upthrust and the downthrust. Well, the upthrust, just from your equation, pressure is force over area. You can see the thrust is the same equation. It's just we were calling it thrust now instead of force. Well, it's the pressure on the bottom, which is given by rho GH. So that is rho density, well actually rho GH, multiplied by the area of a triangle of a circle is pi r squared. The density of our liquid is 900 kilograms per meter cubed, multiplied by G is G, we'll leave it as that. Height here is 6 for the thing, plus 1 more is 7. Plus pi times the radius here is 2 squared. Okay, and I know from doing that earlier, that is 25200 pi g newtons of force acting upwards. The last part of the question says find the thrust on the curved surface, so the force acting downwards. Well, with thrust and buoyancy, the relationship is that buoyancy is equal to the thrust upwards, or the upwards force, minus the thrust downwards. Okay, so that kind of makes sense. You've got an upward force and a downward force, and whatever the net effect is, if it's net upwards, then the thing's going to float. If it's net downwards, it's going to sink. But the buoyancy, is the result of that net force. It will always be net upwards. I'm sorry, if you include weight, you can get a net downward force as well. So the buoyancy is the upward thrust minus the downward thrust. So our upwards thrust, let's rejig that. Let's say move the downwards that we want to the left hand side and the buoyancy that we know to the right hand side. Okay, so we get that it's the upwards thrust minus the buoyancy is what we're looking for, the downward force. So the upward thrust is 25200 pi g newtons minus the buoyancy is 7200 pi g newtons, and that tells us in total it's 18000 pi g newtons is the net downwards force. Okay, so there's 15, and that type of question comes up again in question 14, 16, which uses a frustrum. It's a funny shape. The volume of a frustrum is in the log tables though. 17 and 20 are all this similar type of question. So when you're trying them, you can come back and look at question 15 as an exemplar. Right, question 19 says, given that the relative density of mercury is 16.3, find the mass in tons of half a cubic meter of mercury. That's a very straightforward one. Mass is density times volume is rejigging just density is mass over volume that you had for the junior cert. So density here for mercury is 13600. Okay, so 1,000 times its relative density multiplied by the volume is half of a meter cubed. And again, I did that earlier. So that is 6,800 kilograms or 6.8 tons. Okay, part 2 is the interesting part of this problem. Mercury occupies the curved portion of a fixed upright U-tube of uniform cross-section. Water is poured into one arm and alcohol into the other until both free surfaces, these are the free surfaces up the top here, are at the same level. The lengths of water and alcohol columns are 40.64 and 40.01 respectively. Calculate the density of the alcohol. Okay, so this works on the same principle we've seen before with these U-tube problems, is that along this line here, the pressure and the pressure here have to be the same. Okay, so the pressure at a depth of 40.64 has to be the same. If it wasn't, then one of the columns or the other would move upwards or downwards. So the pressure at this point is easy enough. So we say, sorry, rho 1g h, that's the pressure due to the water. Okay, rho 2g h2 is the pressure due to the alcohol here, and rho 3g h3 is the pressure due to this little bit of mercury that's still above our level here. Okay, so we're going to say the density of water is 1000 g, the height here is 40.64. Density of alcohol is what we want, so I'm going to call that rho g, and the height of the alcohol is 40.01 plus rho here is the density of mercury, 13,600 g, and the height of the mercury, you can see a little calculation here, but just this take away this, leaves 0.63. Okay, and straight away you can see g's cancel in that equation. This is going to be 40640 equals 40.01 rho plus, like I say, I have this done. So this is going to come out as 8568. Move that over and you're going to get yourself 32072 is equal to 40.01 rho. Okay, so just subtracting that from both sides. And then dividing through by 40.01, you're going to get that your density, 32072 over 40.01, comes out as 801.6 kilograms per meter cubed. For the next part of the question, it says more alcohol is then poured in until the two mercury surfaces are level. Find the new length of the alcohol column to the nearest millimeter. Okay, so we're now pouring in more alcohol, so you're going to have more alcohol in terms of volume than you have water until these two are level. But it's the same trick, is that the pressure along that line will have to be the same. Okay, so the pressure from this much water here is going to be rho GH again, 1000 G times a height of 40.64. And that has to be the same as the pressure from the alcohol. Well, we know the density now is 801.6 G times a height of X. Again, G's cancel. X is 40640 divided by this number, 801.6. And it comes out as 50.7 centimeters. Okay, and the last question that I said I'd look at is question 21. Excuse me. A piece of steel floats on mercury in a dish. Water is added until the steel is just covered. If the volume of the steel in water is V1 and the volume of the steel in mercury is V2, and the relative densities of steel and mercury are 7.8 and 13.6 respectively. That's, by the way, why the steel floats. It's less dense. Calculate the ratio of V1 over V2. Okay, so here's a diagram. I have another diagram here. So we have, first of all, I'll just draw your attention that the weight of the object is its volume times its density times acceleration due to gravity. The water has density 1000. The mercury has a relative density of 13.6, which means its density is 13,600. The steel has a relative density of 7.8, so its density is 7,800. In order for this thing to float at this position, the upthrust has to equal the weight of the steel. So the upthrust, well, let's do the upthrust for the section that's in water is the volume of displaced water, V2, multiplied by, it's the weight of displaced water. So that's its volume times the density times G. The upthrust in this section is the weight of displaced mercury. So that's the volume of displaced mercury times the density times G. And that has to equal the weight of the thing, which is its volume, V1 plus V2 together is the total volume, times its density, which is 7,800 times G. Okay, and you can see that G cancels here. This will be the same no matter what gravitational acceleration you're experiencing, if you're on the moon or if you're somewhere else. What do we get out of that? We get, well, 13600 V1 plus 1000 V2 equals 7800 V1 plus 7800 V2. Move this over here. 13600 V1 minus 7800 V1 equals 7800 V2 minus 1000 V2. Okay, so that's 6800 V2. And on this side, if you put that into your calculator, you get 5800 V1. Okay, so to get V1 over V2, we're just going to divide through by V2 and divide through by 5800. We get V1 over V2 is 6800 over 5800, and that will work out as 34 over 29. Okay, so I'd suggest you try a few of the other questions marked with the blue line, the higher level questions, and I'll see you in the next video.